I want to talk a bit more about abstraction and encapsulation. So what I have here is the same basic main function that we've been working with all of these examples involving the rectangle. And of course, this class I've created presents us the abstraction of this rectangle object. So I can ask it for its width, I can ask it for its area. I don't really know what that's supposed to mean deep down underneath, but I don't have to. It's a rectangle to me. And that leads us to this idea of the encapsulation. I guess I'll run this to prove that it works. Okay, there it is. So the encapsulation aspect is that the rectangle object doesn't really tell us what it's doing underneath, nor does it have to. I can ask for its width, I can ask for its height. As long as I get those things, I don't care what it's doing underneath. And what I wanted to show off in this example is when you do it right, encapsulation allows you to make your own decisions under the hood. Nobody on the outside cares. In fact, we could have written code, as we have, using the original version of the rectangle, and then somehow overnight it was swapped out for this strange new alternate version, and we don't even notice, because the encapsulation makes it irrelevant to us what's happening underneath. So I'll show off what's really different about this version of the rectangle. We hopefully can believe the behavior, as far as we're concerned, is the same on the outside to the previous examples. But this rectangle doesn't store its height. Instead, all it stores is width and area. And obviously, if you have the area and the width, you could just divide the area by the width to get the height. And so somebody looking in from outside wouldn't be able to figure out that, in fact, this rectangle doesn't know its own height. It computes it on demand, because the encapsulation prevents it from seeing that. If you ask me for the width, I'll give you the width. If you ask me for the area, I'll give you the area. If you ask me for the height, and you're not trying to pull a dirty trick, then I can just compute the height by dividing the area by the width. Now, it's true there is one sort of issue here, which is that if the area equals 0, when could that happen? Well, it could happen if the width is 0 and the height is anything. So we don't know what the height is if the area is 0. Or it could happen if the height is 0 and the width is anything. So if the area is 0, we'll just assume the height is 0 and then return it. And we'll think in a minute about how we could solve that problem in a more elegant way. If you try and create the rectangle, and I'll go back down to main to show off that this is the same code we were running before. When I create the rectangle, I tell you the height, I tell you the width, and the area comes out to be 60. So you have no way of knowing that secretly the rectangle is just dumping the height as soon as you pass it in. As far as you know, it is storing the height, because you can pass it in and you can get it back. When you pass the height in, so we get the initial width and the initial height, it just computes the width, and then it computes the area, and then it just ignores the height. And when you ever ask for the height again, it computes it from the area. And from the outside, you have no way of knowing because everything is encapsulated. But wait a minute, what about that case where the area is 0? You know what? Actually, all this time, we've been trying to prevent our rectangles from having a negative width or height. Maybe we should also prevent them from having a width or height of 0. It's not really a rectangle if its height is 0, is it? It's more like a line. So we could do that. I guess there are a couple of options. One thing I could do is I could say you cannot create a rectangle with a width or height that is less than or equal to 0. Okay, so that's one way of preventing a rectangle from having a 0 width or height. The problem is it doesn't fix everything, because if I call the default constructor, it still initializes a rectangle to have a width, and in this case area, of 0. So what do I do? Well, one option would be the cop-out, and just to say, look, if you construct a default rectangle, we'll make that a unit square. Okay, so we could do that. That's a bit disgusting, though. Who's to say what a default rectangle is supposed to be? If it's not going to be 0, 0, why should it be anything? So one other option would be to say, wait a minute, if you want a rectangle, you have to tell me the width and height. I'm not going to let you create a rectangle with the default constructor. I'm making the default constructor private. So the rectangle class gets complete control over how and when it gets created and who gets to create it. So if I decide that it makes no sense to have default rectangles with a 0 width and height floating around, I can prevent that. I can make it impossible to create a default rectangle. So we'll try that. And we'll notice, because the default constructor is private, if we go down to main, on line 59, where I try and create a rectangle using the default constructor, I am not allowed to. The compiler prevents me because that constructor isn't available to me. That constructor is private, and therefore that object cannot be created. So if I want to prevent people from making a rectangle with 0 height and width, I could force the parameterized constructor to ensure that the rectangle's width and height are positive, and then I can force anybody trying to create a rectangle to use only that constructor. They're no longer given the option of making a default rectangle. If you want a rectangle, you have to provide the width and height yourself. And so it's another way we can use the access control mechanism to impose arbitrary constraints on how the type is used. And it also shows off that if we write our class correctly, from the outside, it may not be clear what we're doing, and we could even change what we're doing at any time because we're using encapsulation.